Good day, students, and welcome to this clip on solving absolute value inequalities. Before we start going over two examples that we're going to do today, we're going to focus on classification. How can we classify the whole set of absolute value inequalities and also equalities? So we're going to make a table, and we're going to use that table to classify our absolute value inequalities and equations. All right. So let's partition it like this. All right, we're going to break it into three categories. We're going to have the bounded region in one, and then we'll have the boundaries in one, the unbounded regions in two, and then the bounded regions in the last one. Okay, so it's classified as follows. In the first area, we're going to have boundaries, and then we'll have, in the middle, we have bounded. Another word for bounded is sandwich. Okay, sandwich. And then on the last area we have unbounded. Okay, unbounded. All right. So the first thing we're going to be looking at is the general form. The equation in general form. For each category, what does the equation in general form look like? So let's go ahead and create it. In general form, boundaries are basically equations, okay, are absolute value equations. So it's in the form absolute value of x minus h equals r. All right, h is the center, r is the radius from the center. For bounded regions, it's going to be absolute value of x minus h less than r. This less than basically means you're within the boundaries, okay? And note, these two can be combined together, and then if you combine them, you have less than or equal to. So it's going to be the bounded region plus the boundaries, all right? And then unbounded is going to be the flip of this. It's going to be the absolute value of x minus h is greater than r. All right? Greater means you're not restrained, you're not constrained by the boundaries. You just go in one direction forever, whatever direction it points in. And also note that unbounded regions can be combined with boundaries, and in that case you have greater than or equal to. Okay? So this is the general form of the three absolute value scenarios we're going to be dealing with. We already worked on this last lesson. We're going to be dealing with these two in this lesson, alright? Okay, now that we know what the general form is, we're going to look at how the solutions look like, alright? So we're going to start by looking at the solution in combined form, combined form. All right. So what does a solution in combined form look like? Uh, well, it turns out that there's only one of these three absolute value equalities, and inequalities have a solution in combined form. All right. So for the boundaries, since they're boundaries that are not continuous or contiguous, there's no way you can express them in combined form. So for boundaries, they're none. For bounded regions, in combined form, you write it as a is less than x and x is less than b. All right? And what does the graph of that look like? Well, you just have your number line. You have the lower bound, which is the left of the inequality, which is a, and then the upper bound, which is b. And then guess what? You're going to be bounded between these two open circles right here. And that's what the graph of this bounded combined inequality solution looks like. All right. So the solution set for this problem is anywhere between a and b will work to satisfy this equation. So this is the solution to this equation in combined form. All right. We can combine it with boundaries that just fills in this circle, okay? But this is strictly unbounded. This is strictly bounded, so that's why I have open circles here. For unbounded, since they're not bounded by anything, there's no way you can write the solution in combined form. So they're none for this. Okay? Alright, how about solution in separate in separated form. Separated form. If I want to write it as a set of two distinct equations or inequalities, how can I express the solution? That's the question. Okay. All right. So let's take a look at the absolute value equations. The absolute value equations, when you solve it, standard answer that you normally get, which are x equals a or x equals b. Okay. And if you wanted to graph that, you just have your number line, and then you have the two boundaries. The lower boundary, the one to the left, is A, and then the upper boundary is the bigger one, B. You have a closed circle on the left and a closed circle on the right. Okay? So this is separated because you have one equation here and another equation here, as opposed to this that you just have one equation that has a combination of two equations. Alright, so that this is the separated form for solving absolute value equations. Now how about for a bounded region? For a bounded region, the separated form, you're going to have x is x is greater than a, x is greater than a, and x is less than b. Notice here you have an and here, and this one you have an or. This and basically means it's a sandwich situation. So you see the sandwich and this and there. Remember, anytime you have a bounded region, it's always an and if you want to write it in separated form. Alright? And then to graph it, the graph of this solution is going to be exactly the same as this one right here, okay? So the graph is going to look like this. Since x is greater than a, you have your lower bound to the left side, which is a. Your upper bound is b. So you have two open circles here because you have no lines. It's not combining with the boundaries. And then anywhere within these two boundaries will satisfy this separated inequality right here. Alright, so this is how it looks like, exactly the same as that. Alright, when we go to the absolute value the unbounded regions, it's a little bit more extensive. You have four possible cases or four separated formulations that you can use here to write this equation, to write down this equation, okay? All right, so let's go ahead and do it. So for the first case, you can have x is less than a or x is greater than b. In that case, you're going to have, this is the first separated form, you're going to have the arrows pointing in different directions, okay? The lower bound is a, the upper bound is b. So for x is less than a, you're going to start from a, open circle, and then you'll be going all the way in the direction of the inequality, which is to the left, like that. Alright, so that's x is less than a. For x greater than b, you start from there, and then you're going to be going all the way there. Alright, so that's scenario one for the separated form of the solutions for absolute value inequalities which is greater than. Second possible scenario is you can have x is less than a or x is less than b. You notice they both point in the same direction, okay? But remember, when you're dealing with unbounded regions, you don't stop at the boundaries. You run right past the boundaries. That's what the whole idea of being unbounded is, okay? So in this case, lower bound is a, upper bound is b. So starting from a, this one says less than, it goes to the right. I'm going to put the two circles here. So for the first one, less than for a means you're going to the left. And then this one is also less than, guess what? That means it goes right past over a, and you have something like this. So you have a line going, everything pointing going to the left. So that's case number 2. And then case number 3, for the unbounded regions for absolute value inequalities, is when you have x greater than a or x is less than b. Okay, it's like the opposite of this. So what on earth does that look like? They're going to be facing the same direction, right? They're going to be facing each other. So how is the graph going to look like is a question. All right, remember that this is unbounded. Whenever you think of unbounded or greater than, you don't stop at the boundaries. You run right over the boundaries. All right, so this one, you have A and you have B. This is the first one. There goes the second one. Open circle because there are no lines under the inequality. So for the first one, it says x is greater than a, so that means you're going to go to the right. So you're going to go right over b, bam, like that. All right? And then this one is less than b, so you're going to go to the left. So for this one, you're going to go right over a, and like that. So this one includes everything. Whenever I have an unbounded region of this nature, the entire number line will work for this. Okay? All right, and then the last scenario that we have for unbounded regions, scenario 4, is you have the opposite of case 2, where you have x is greater than a, or x is greater than b. Okay? All right, so what will the graph of that one look like? So you have your number line, and then the lower bound is a, and your upper bound is b. Have circles on both sides. So they're both pointing to the left side. They're both pointing in the same direction. So for the b, it's x is greater than b. It points in that direction. And then x is also greater than a, so it also points in this direction. But it runs over b, I'm sorry, and then goes in that way. Okay? So your 4 cases for absolute value, for unbounded absolute value inequalities are either they're broken apart like this, they all go to the left, the whole line, or they all go to the right. So these are the cases. Okay, so just by looking at the graph, you can know if the equation is less than or greater than. All right, so remember, and is for bounded, ors are for unbounded and boundaries. All right, now with this classification in mind, let's go ahead and try out some examples. So we're going to write down the instructions first, and then do some examples. So these are the instructions. Classify B, absolute value inequality, solve it, graph, solve it, graph, and test your intervals for accuracy. Test your intervals just to make sure your answer is correct. Test your intervals for accuracy. Okay? All right. So remember, when you're solving absolute value inequalities, you don't get fixed point answers. You get intervals as your answers. Okay? So let's try the first example, number 1. What if we have the absolute value of x minus 3 is less than 5? All right. So first thing you want to do is you want to classify it. Classify. Is this boundaries, bounded, or unbounded? We'll go up to our table. You notice that less than is bounded because you're within the region. Okay, equal is boundaries, greater than is unbounded. All right, so the classification of this is bounded. All right, so we know what our graph is going to look like. It's going to look like a sandwich. All right, so there you have it. Now let's go ahead and solve. So to solve this, we're going to have the absolute value of x minus 5. Oops, sorry, x minus 3. X minus 3 is less than 5. So absolute value means distance from 0 from the left or right. So that means we're going to replace this absolute value quantity with plus or minus. X minus 3 is less than 5. Okay? That's how you replace the absolute value. Now, we're going to break this apart. We're going to have the negative and the positive. Negative to the left, which is x minus 3 is less than 5. And then we're going to have the positive on the right, which is x plus 3 is less than 5. Okay, what on earth did I just do? Well, exactly what we did in the previous example. In the previous clip, the negative one goes to the left side and the positive one goes to the right. Okay, so Keep that in mind. I put the plus here, and I put the minus here. So we have two separated inequalities that we're going to solve independently, okay? All right, now let's go ahead and solve this. So for this one, we're going to have distribute the minus. We'll have negative x plus 3 is less than 5. And then to finish this one up, it's a two-step process. We subtract 3 and divide by negative 1. So let's go ahead and do that. Subtract 3 from both sides. And then you have negative x as less than 2. And then you divide by negative 1. And then your final answer is going to be x is greater than negative 2. Notice what I did here. Anytime you divide by negative, what happens with the inequality? It flips because you're reflecting the number line, so you have to keep that in mind. On this side, I can simply drop the absolute value because there's no signs in front. X plus 3 is less than 5. So I subtract 3 from both sides. Subtract 3, subtract 3. And then you have x is less than 2. And that's your answer, okay? So the question is, am I going to use an and or an or to combine these two inequalities? This is a sandwich, remember, a bounded is a sandwich, okay? So that and is like a giveaway. Whenever you have a sandwich solution, it's an and, so this is an and, all right? So this is a solution in separated form. I also need a solution in combined form. What the solution in combined form is going to be negative 2 less than x less than 2. So anytime you have a bounded scenario, I would like you to give me the answer in separated form and combined form, okay? Because bounded inequalities are the only ones that exhibit this unique property. All right, so we have the solution. Now let's go ahead and graph. All right, let's do a graph. So let's make our number line, and we're going to sketch what the solution looks like. All right, so there goes your number line. Let's put in 0 at the center. That's 0, 1, 2, 1, 2, and then negative 1, negative 2. There are no lines under the inequality. It's strictly bounded. It's not bounded plus boundary. So you have open circle on the left and open circle on the right. And then since it's sandwiched between negative 2 and 2, all we simply do is just fill in the center area right here. So from here to there, down. There goes your answer. That's the graph. Okay. Now that we're done solving and graphing, we have to test to see if our interval is correct. So the last piece here is a test. Okay, we're going to do a test. Now we have only one interval to test, which is the interval here. We call it interval 1. In some problems, we might have more than one, okay? So we have one interval to test here. So we can pick any number between negative 2 and 2. You cannot pick the endpoints because you have an open circle. So any number here will suffice, okay? So I'm going to test with the easiest one, which is 0. So I'm going to test with x equals 0. So what I'm going to do is I'm going to take x equals 0, and I'm going to plug it into the original problem. If I get a true statement, that means my answer is correct. If I don't, then that means my answer is wrong. So let's do the test. So I'm going to plug this put this x value into the original problem. All right, so let's do a test. We're going to have 0 minus 3. Is 0 minus 3, the absolute value of 0 minus 3 is less than 5. The absolute value of negative 3 is less than 5. Absolute value of negative 3 is 3. Question is 3 less than 5? Absolutely. So that checks out perfectly. So that tells me that my original answer is correct. All right? So there you have it. Okay, let's try another problem. Example number 2. We're going to be doing exactly what we just did. We're going to solve, graph, and then test the accuracy of our solution using an interval, okay? So in this case, we're going to be dealing with the absolute value of 2x plus 1 greater than or equal to 7. All right, so we're going to start out by classifying the absolute value inequality that we have. This one is greater than or equal to. So what's the classification going to be here? we're going to consult our chart in a minute. So to classify this, let's go for a minute, all right? If you're strictly greater than, it's unbounded. But this one is greater than or equal to. So it's a combination of this one right here and that one right there, all right? So boundaries and unbounded, we're going to have them combined in this problem right here, okay? So for the classification, it's going to be um, unbounded for the greater than, unbounded plus boundaries, plus the boundaries, okay? Boundaries. All right, so anytime you have a line under an inequality, you always have to add the boundaries to. What it basically means, instead of just having open circles, the open circles becomes filled up because of that equal to, okay? Because the equal to tells you that you have to include the endpoints, all right? So this is unbounded plus boundaries. Unbounded, let me just put a side note here. Unbounded is for like the greater than component, and then the boundaries part is that. So if I combine these two inequalities together, I'm going to have greater than or equal to, all right? So that's the classification. All right, let's go ahead and solve it. Okay, so to solve this, we have the absolute value of 2x plus 1 is greater than or equal to 7. Now, absolute value is distance from 0 to the left or right, so we're going to replace this absolute value with plus or minus 2x plus 1 greater than or equal to 7. The plus basically means the distance of this quantity to the right is less than that, is greater than that, and then this minus means to the left. Okay, so what we're going to do now is we're going to split this combined equation into two. It's combined because we have plus or minus, which is a 2 in 1. So we're going to have negative on the left side, negative 2x plus 1, greater than or equal to 7. Please keep the parentheses. And then we're going to have 2x plus 1, greater than or equal to 7. Okay, what did I just do? I just basically splits the inequality. I put the minus here, and then I put the positive one on the right. Okay, so I like to do this so that I don't make mistakes when I'm solving the problem. All right, so positive, negative to the left, positive to the right. We're going to solve them independently, and that will give us our solution. Okay, so for this one, I'll distribute the negative to both sides of this quantity, of the two terms in this quantity. So we have negative 2x minus 1 is greater than or equal to 7. All right, now to solve this, we can do this in two steps. We divide by we add 1 to both sides, and then divide by negative 2. All right, so let's do it. You add 1, and then that gives you negative 2x is greater than or equal to 8. And then you divide both sides by negative 2. So divide by negative 2, divide by negative 2. And then you have, now note, anytime you divide by greater than, divide by negative, the inequality switches. So instead of it to be greater than or equal to, it's not going to be less than or equal to negative 4. Okay? So there goes one of the upper bound of the lower unbounded region. And then for this one, there's no minus there, so you have the 2x plus 1 greater than or equal to 7. To solve this, you basically do two steps. You get rid of the positive 1 by subtracting 1, and then divide by 2. Okay? So subtract 1 from both sides, and then you have, you'll be left with 2x is greater than or equal to 6. And then lastly, divide both sides by negative 2. And then you have x is greater than or equal to negative 3. Okay? I'm sorry. Divide both sides by, where did that negative come from? Divide both sides by 2. Put in stuff there. Anyway, divide both sides by 2, so you have 6 divided by 2, you have 3. Yeah, there you have it. Is this an and or an or? Well, let's go back to our inequality again. Remember, the only one with an and is a sandwich, the bounded region, less than. Okay, the other two are ors. So you have an and here. This one is or and or. This one, all of them is or. So keep that in mind, okay? So since this is unbounded, it's going to be or. Okay, so our solution, the solution for this one is going to be x is less than negative 4, or x is greater than 3. If you think about it, there is no number that is less than -4 and greater than 3. It doesn't make any sense, okay? It has to be one or the other since they're disjointed, okay? All right. Now, what is the answer in combined form? Unbounded inequalities do not have solution in combined form, okay? You can't combine two disjointed intervals, all right? So you just have separated form, and that's it. All right, let's go ahead and graph the solution. Let's do the graph right here. All right, we're going to graph it. So make our number line. And let's calibrate our number line. Starting with 0, I'm going to go left all the way to -4. 1, 2, 3, 4. That's -4. And then right all the way to 3. 1, 2, 3. That's 3. And then you have it for the two boundaries there. Now, since you have less than, that means your arrow is going to point to the left. Okay, less than means to the left, and greater than from 3, your arrow points to the right. Okay. Now note, you also have this line under here. What on earth does this line mean? That line basically means that the boundaries have to be included. Remember, we said that the classification was unbounded plus boundaries, so we have to include the boundaries, which are those two dots. So we have to fill in this and fill in that, which means that these points are part of the solution set. Okay, if you want to do a test, you can include those points. It's okay. All right. Now that's our graph. Now that we're done solving and graphing, now what we're going to do next is we're going to test. We're going to do a test to see if our graph is correct. We're going to test the interval test. Okay. So now this is unique because guess what? We have two intervals. We have interval 1 and we have interval 2. Okay. So we have two candidates that we must test to make sure our answer is correct. So what I'm going to test is I'm going to pick, how about we pick -5. I'm going to use -5 as my first test subject, and I'm going to use, how about I use 4 as my next test subject, okay? Why did I pick 4 and -5? Well, because this solution is telling me that anything to the left, 4 and to the left, is good, is game, okay? So -5 is to the left, so that's why I picked -5. And I can pick 4 here because anything to the right, from 3 to the right of 3 or greater, is good. All right, so these are my two test values I'm going to use to check if my answer is correct. All right, so let's test interval 1. So tested interval 1. For interval 1, we're going to be using the candidate x equals -5, and we're going to be plugging it into the original problem. We're going to be plugging it into the original equation, which is, let me put it up here. The original equation is 2x plus 1 greater than or equal to 7. All right, so I'm going to plug in x into that. So the question is 2 times -5 plus 1. If I take the absolute value of that, do I get a number that's greater than or equal to 7? Do I? 2 times 5 is 10, -10 plus 1. Is the absolute value of -10 plus 1 greater than or equal to 7? Advancing, we have the absolute value of -9. Is it greater than or equal to 7? Absolute value of -9 is how far -9 is from 0 on the number line, which is 9 units. Is 9 greater than or equal to 7, is it? Absolutely. So, check. That one works nicely. Are we done? No, we have to test two intervals, right? Because our solution includes two intervals, so we have to test interval number 2. All right? Let me partition my workspace so that we don't get mixed up. All right, so my second candidate that I'm testing is x equals 4. Okay, so is the absolute value of 2 times 4 plus 1 is it greater than or equal to 7? What did I just do here? I just plugged in 4 into the original problem, and I'm trying to see if I get a true statement. If I do, then I'm good, okay? So 2 times 4 is 8. Is 8 plus 1, if I take the absolute value of that, is it greater than or equal to 7? 8 plus 1 is 9. Is the absolute value of 9 greater than or equal to 7? Absolute value of 9 is how far is 9 from 0 on the number line, right? Which is 9. 9 units. Is 9 greater than or equal to 7? Absolutely, we already established that right here, right? So that checks out. So since my two intervals are good, that means that my original answer is correct. All right, so thanks so much for paying attention to this presentation. All right, please feel free to subscribe to my videos, or you can share this with your friends on Facebook, Twitter, or Google+. And also feel free to request videos on the comment section down here. More videos can be found on mycoachserve.com. Thanks again, and have a wonderful day.